Hey guys, this video is the first in our new chapter, chapter 17 in the Silberberg APChem book, about chemical equilibrium. And chemical equilibrium tells us the extent of a chemical reaction. An example we might use is the transition between two gases. N2O4 dinitrogen tetroxide. This gas, if you introduce it into a flask, is colorless. I'll put colorless underneath it. So if you put this gas into a flask, this gas is colorless, which we will indicate here with these circles with no color inside of them. Now, if you introduce this gas into a flask, this gas immediately starts to turn into another gas, nitrogen dioxide. The difference between these two gases is that the nitrogen dioxide is a colored gas, and it's actually brown in color. So what you start to notice is that some of these gases actually form a dark brown gas. Now, because one of these, N2O4, transitioned into two NO2 gases, I'm going to show one of these here, circles, going dark, and then another dark circle is going to pop up as this gas decomposes. But what can happen is the backwards reaction also. And some of these darker gases of nitrogen dioxide will actually start transitioning back to colorless gases. And eventually what's going to happen is you reach a point of equilibrium where the rate going in this direction, the decomposition, eventually equals the rate going in the opposite direction for the synthesis. I'm going to call this rate 1, or rate, actually I'll call it F for rate forward, and I'll call this rate sub B for rate backwards. Eventually, you don't see any more change in the actual numbers of these gases. Because if the rate forward eventually equals the rate going back, you will get what seems to be a static situation, where the actual number of dark molecules here and colorless molecules stop changing. The reality is that this is a dynamic process, and you still have transitions happening this way and this way. However, the rates of the transitions eventually equalize, and because the rates eventually equalize, the number of molecules stays constant. Another way you might think about this is the transition between, let's say if you introduce liquid water into a cup, that liquid water will eventually start producing gaseous water, but then some of the gaseous molecules will also transition back into the liquid phase. You eventually reach a point at which the rate forward equals the rate back, and you no longer have a change in the number of gaseous water molecules over the liquid water. That is the equilibrium vapor pressure of the gaseous water at that temperature. So chemical equilibrium, while it seems to be a static process, is actually quite dynamic. What happens is a reaction in which you can go in one direction is matched by a reaction in the opposite direction. Now here is what it doesn't mean. It doesn't mean that the number of molecules of NO2 equals the number of N2O4 molecules once equilibrium is reached. The pictorial representation down here shows two of these dark molecules and 1, 2, 3, 4, 5, 6 of the colorless molecules. Equilibrium may be reached in that state, where there's only 2 dark and 6 colored. It's possible that there are equal numbers at equilibrium, but it's unlikely statistically. The same is true here with the water molecules. Just because equilibrium is reached, what it does not mean is that the same number of water molecules are in a gaseous state as there are in a liquid state below. In fact, there will be far, far more, in this particular case, liquid water molecules than you'll have gaseous water molecules above. Again, equilibrium only means that the rate going in one direction eventually equals out to the rate going in another direction. What that ends up doing is creating a ratio. It creates a ratio of the number of these molecules on the right-hand side of an equation compared to a ratio, divided by the ones on the left. In the next video that we'll talk about, we'll start getting into the math and how that works out mathematically. But this first video, I just want you to understand this concept. Another way of thinking about this is a graph of concentration over time. At the very beginning, if we look at this graph in respect only to the N2O4, what we're going to see is over time, this concentration decreases. And once it starts to level off is the point at which equilibrium is reached. At the same time, if there were no N2O molecules to start, its concentration would increase over time. Notice that they start to level off at the same place. When they level off, we have reached a point of equilibrium. Notice also that this graph might have been somewhat different. It's possible that the N2O4 remained in greater concentration at equilibrium, and the NO2 remained in lesser concentration at equilibrium. Whichever substance shows the higher concentration at equilibrium is the one obviously in greater population. When these lines start to level out, that's when equilibrium has been reached. Another way we can look at this reaction is from the perspective of kinetics. We've talked about how the rate forward equals the rate back once chemical equilibrium has been achieved. Using what we now know about kinetics, the rate is going to be equal to the rate constant going forward of N2O4 and the rate law does show that NO2 is squared K forward over K reverse equals NO2 squared over N2O4. And K forward over K reverse is often called a capital K, which we now call the equilibrium constant. Sometimes it is written KEQ. The large K is called the equilibrium constant. And there's a subtle point to be noticed here. Just because the rates equal one another does not mean that the rate constants equal one another. KEQ is the rate constant. If KEQ is a large number, greater than 1, what that means is the products, if I can spell product, I'd be better off. Let's see, P is greater than 1. That means the product concentration is much greater than the reactant concentration at equilibrium, because that means the numerator is much greater than the denominator in this ratio. However, if the equilibrium constant is rather small, let's say much less than 1, this tells us that the opposite is true. That the product concentration is actually much less than the reactant concentration. This ratio here is reversed. If this number on top is small, divided by something large, then what we have is a small number. So the equilibrium constant, by virtue of its size, can tell us in this equilibrium whether we have more amounts of products or more amounts of reactants. If the equilibrium constant is large, it is said to lie far to the right. To go back to our original equation, lying far to the right means that there's a lot of product and not a whole lot of reactant hanging around at equilibrium. If, however, the equilibrium constant is small, the equilibrium is said to lie largely to the left. And what that means is there are large amounts of reactant and actually very small amounts of product at equilibrium. So to summarize, chemical equilibrium is a dynamic process. Some reactions can actually go backward after some of the product builds up. Some of it can react back and go backwards. This is represented by a double arrow and expressed with equilibrium. When we look at the equilibrium concentrations, a couple different factors can be true. If the reactants stick around in higher quantities, then what we're going to see here is a small KEQ. If, however, the product concentrations are larger than the reactant concentrations, whoops, oh, it looks like NO2 here was a product. I made a mistake. So the KEQ here would be larger than 1. This would be the opposite scenario because this was our reactant. If the reactant concentration remains in greater quantity than the product, then KEQ is going to be on the smaller side. So by virtue of KEQ, what we have here is, in fact, a good indication as to whether or not our reaction lies to the right or to the left. If KEQ is large, we have more product than reactant, and if KEQ is small, we have more reactant than product. And if KEQ is around 1, well then we have relatively equal concentrations of reactant and product, because sometimes we have exponents here in our expression that can actually end up changing things from that value of 1 a little bit. So that right there is the introduction to chemical equilibrium. We're going to get more into the math in the next video.